In this lecture, we're going to take a look at the driving forces that act to move molecules around. There are three different types of driving forces that act to move molecules. The first one is the chemical driving force. And this one you've already learned before. This one is the same thing as the concentration gradient. So remember that molecules like to move from high to low concentration. And the second one is the electrical driving force. And this one only acts on ions. So if it's not an ion, you don't have to worry about the electrical driving force. So this one has to do with the membrane potential, which is talking about the charges that are inside the cell and the charge on the ion. And then the electrochemical driving force, if you look at the name, it has electrical driving force and chemical driving force in it. So you're just going to add up the electrical and driving forces together. All right, so let's take a look at the chemical driving force first. This one's easy, you've learned it before. This is just the concentration gradient. Remember that molecules like to move down their concentration gradient. So they want to move from areas of high concentration to areas of low concentration. So you can see in this picture from your textbook, we've got a higher concentration of these red molecules inside the cell than we do outside the cell. So our chemical driving force is going to be out of the cell. And the other thing with the chemical driving force is that if you have different molecules that you're looking at, each molecule doesn't care what the other one is doing. So that makes things really easy for us. So like if you're looking at sodium and glucose in a cell, the glucose does not care what sodium is doing. So the glucose molecules are just going to look at their own concentration gradient, and so they're going to move from high glucose to low glucose concentration. So their chemical driving force would be out of the cell for glucose. And then sodium will just look at its own concentration gradient, and so it would move from high to low sodium concentration. So the chemical driving force for sodium would be into the cell. And then I just to keep these driving forces straight, I just put a C just to remind myself that that's the chemical driving force. Let's look at two more examples of the chemical driving force. The top example, we have a concentration outside the cell of whatever molecule this is of 21 millimolar. And then we have a concentration inside the cell of 83 millimolar. So we'll just draw this out. It's always good to draw pictures of things. So when you're taking the test, I definitely would be drawing pictures. So the concentration outside the cell is less. So we'll just say, I don't know, maybe this is ion X. Okay, so we have less outside the cell and we have more inside the cell. Okay. And so we've got 83 millimolar inside and we've got 21 outside here. And so our chemical driving force, this ion would just move down its concentration gradient going from high to low concentration. So the chemical driving force will be out of the cell. And then our next example on the bottom here, we've got a concentration outside the cell of 145 millimolar. And this is actually the concentration of sodium. So we'll draw some sodium here. So that's 145 outside. And then the concentration of sodium inside is a lot less. It's at 15 millimolar. And so the chemical driving force, sodium just wants to move down its concentration gradient from high to low concentration. So sodium would want to move into the cell down its concentration gradient. So the chemical driving force would be into the cell. And if you wanted to compare the strength of the chemical driving force between these two different ions here, if you just look at the difference in the concentration gradient, the larger the concentration gradient is, the bigger the chemical driving force is going to be. So you can see in our top example, you've got a difference of 83 and 21, so you've got a difference of 62 here. And then in our bottom example with the sodium, you've got a difference of 145 and 15. So if you subtract those, you've got a difference of 130. So you've got a much bigger concentration gradient with the sodium than you do of whatever this ion X is. So I would actually draw a much thicker arrow over here with the sodium just to show that, hey, I've got a much larger concentration gradient with the sodium compared to whatever ion X is. And so the chemical driving force for sodium is actually a lot stronger than it is for that other ion X. Okay, just because the larger the concentration gradient is, the larger the chemical driving force is going to be. Okay, and I know that you guys have learned that before when you've talked about concentration gradients. Okay, let's take a look at this electrical driving force. I know this is new. Notice at the top here, I have highlighted in yellow, underlined, capitalized, and put in exclamation marks that this electrical driving force only applies to ions. Okay, so that's really important to remember. So if it's not an ion, you don't have to worry about this electrical driving force. So if you have something like glucose, or water, or oxygen, carbon dioxide, anything that is not an ion, it does not have a plus or a minus charge on it, you don't have to worry about this electrical driving force. Okay? All right, so this electrical driving force has to deal with the membrane potential, okay, which is talking about the charges inside the cell, and also has to deal with the charge on the ion itself. So you're just looking at the charges inside the cell and then the charge that's on the ion. Okay, so that's what we're going to be looking at. All right, so what exactly is a membrane potential? The membrane potential, there's just a difference in ions inside the cell versus outside the cell. Okay, and so there's a difference in voltage across the cell membrane. And so we abbreviate the membrane potential V sub m. The V just stands for voltage, and the little m just stands for membrane. Okay, so that's where that came from. And having this difference in charges in what's inside the cell versus what's outside, it's kind of like a battery. So when the ions actually do start to move across the membrane, it actually creates an electric current. Just like what happens in a battery, like when you turn the flashlight on, the ions actually start to move and create an electric current. And that's the same thing that can happen in a cell as well when the ions actually start to move. All right, so how we draw this membrane potential. If the inside of the cell has more anions, and remember an anion is a negatively charged ion. And the way I remember that is the word anion has an N in it, and I just remember negative charge, okay? So if there's more negatively charged ions inside the cell than outside, that means that your membrane potential is less than 0. It's going to be a negative number of some sort. Maybe your membrane potential is minus 70 millivolts, or maybe it's minus 20 millivolts, or whatever it is, okay? And so we're going to measure this membrane potential, this V sub m, in millivolts. Okay, that'll be our units. So when I draw this, I'm just going to draw negative charges in here. Okay. Now there are some positive charges inside the cell, but I'm not going to draw those. And there are some positive and negative charges outside the cell, but I'm not going to draw those either because you're going to get confused. All right. So we're just concerned about, hey, there's more negative charges inside the cells than there is outside. And so we just want to draw these negative charges inside. That's all we're going to draw. Okay. Your membrane potential can also be positive. So if you have more cations, remember a cation is a positively charged ion. And the way I remember that is cation has a T in it, and a T looks like a plus sign. And so that'll help you remember that a cation is a positively charged ion. And so the way I would draw this is that if your membrane potential, your V sub m, is greater than 0, meaning that it's positive, maybe your membrane potential is plus 30 millivolts, or maybe it's plus 60 millivolts, whatever it is, then I would just draw some plus signs in here. Okay. And you don't draw what's on the outside. You just draw that, hey, we've got more pluses on the inside than we do on the outside, and that's all we're concerned about. So that's all we're going to draw. Because if you start drawing what's on the outside, you're going to get confused. Okay. You can have the membrane potential equal to 0. And when that happens, you have an equal amount of anions and cations, so plus and minus charges inside and outside. And so you wouldn't draw any charges inside the cell at all, okay, because you have an equal amount of pluses and minus inside versus outside. Okay, so that's how you would draw the cell if the membrane potential were equal to 0. Okay, all right. Okay, so that's really important on how to draw the membrane potential. So only draw what's going on inside. Don't be putting stuff outside, because otherwise it's going to get you really confused. All right. Okay, so this is, realistically what's going on with the cell. This picture from your book is showing you inside the cell on the left, showing you the intracellular fluid, and it's just showing you that there's more anions, more negatively charged ions inside the cell than outside the cell. And so for many of the cells of the body at rest, the resting membrane potential, so that's what we call it when these cells are at rest. And what we mean by at rest, it just means that they're not sending or receiving any signals. They're just sitting there at rest, not doing anything. And for many of these cells, the resting membrane potential is minus 70 millivolts. Okay, so that's a good number to memorize because we'll be talking a lot about that with the neurons in chapter 7. Okay, that resting membrane potential. So how I would draw that is I would just draw these negative charges inside, and that's all I would draw for a resting membrane potential of minus 70 millivolts. Okay. All right, so let's take a look at this electrical driving force. All right, so two things you need to look at for this electrical driving force. One is you need to look at that membrane potential. Is it negative or positive inside the cell? And then also you need to look at the charge on the ion. Okay, is it positive or negative? Okay, and that'll determine which way the electrical driving force is going to be pushing that ion. And just, this is really important to remember, kind of a rule of thumb, is that opposites attract and like charges repel each other. Okay, so that would be really good to remember. And just remember that if it's not an ion, you don't have to worry about this electrical force. So if it doesn't have a full charge on it, you don't see a plus or a minus on it, it's not an ion, then you don't have to worry about this. So if you have something like glucose, or you've got water or oxygen or carbon dioxide, you don't have to worry about an electrical driving force, okay, because they're not an ion, and so there's no electrical driving force for them. Okay, so let's do an example of looking at the electrical driving force. All right, so let's say that the membrane potential is less than 0, which means it's going to be negative. So I would first draw my cell with some minuses in here, indicating that we've got a negative membrane potential. And my ion here, I've got some potassium, okay? And potassium is always higher inside the cell than outside. And we actually don't need to know the concentration gradient because we're just looking at just the electrical driving force, okay? But we'll just draw it in here anyway. Okay, so looking at the electrical driving force, we're just looking at just the charges. Okay, we don't care about this concentration gradient at all. All right, so looking at the charges, inside the cell we've got these negative charges, and then on the potassium we've got a positive charge. And remember that opposite charges attract each other. So this potassium that's outside says, hey, I would love to come in there and be with those negative charges. And the potassium that's inside the cell says, I want to stay in here and stay by these negative charges. So this electrical driving force would be into the cell. Okay, and I just label the electrical driving force with an E just to remind myself that, hey, this is the electrical driving force, okay, and not the chemical driving force. Okay. Now, what if I said instead that the membrane potential was greater than 0? Okay, meaning that it was positive. So we would draw some plus signs in here. Okay, and we'll draw our potassium. Okay, and remember that like charges repel each other. So the potassium that's inside the cell says, I want out of here. And the potassium that's outside says, no way, I'm going inside there. And so in this case, if the membrane potential were greater than 0 or positive, then the electrical driving force will be out of the cell. Okay, because those like charges repel each other. They don't want to be by each other at all. Okay. All right, so a couple of things affect the magnitude or size of the electrical driving force. So it depends on the size of the membrane potential and the amount of charge on your ion. Okay. All right, so we're just going to draw these out and just show you how this works. All right, so first of all, we're going to look at changing the membrane potential. All right. So here we've got some sodium, and we've got a membrane potential of minus 50 millivolts. All right. So I've drawn my cell with some minus signs in there. Okay. And here's my sodium. And we could certainly draw the concentration gradient for sodium, although we don't need it because remember we're just looking at the electrical driving force and we're just looking at the charges right now. Okay, but looking at our electrical driving force, looking at just the charges, okay, sodium with a positive charge and this minus charge from the membrane potential inside the cell, opposite charges attract each other, and so this electrical driving force would be into the cell, right? Okay, because the positive charges want to be with the negative charges inside there. So sodium that's outside would want to come in. The sodium, if it's inside, says, I don't want to leave, I want to stay here. Okay, so it would be into the cell, okay, with this electrical driving force. And then if we change our membrane potential, we make it even more negative. We make it minus 100 millivolts. So we've added even more negative charges inside the cell. So I would just put even more negative charges than I did at minus 50 millivolts. And got our same amount of sodium here. And now if you look at our electrical driving force, sodium says, oh my gosh, I really want to go into that cell now. Even more than I did over here when it was at minus 50 millivolts. Because now there's even more negative charges at minus 100 millivolts than there was at minus 50 millivolts. So I would draw my electrical driving force as a thicker arrow, indicating that you've got an even stronger electrical driving force than you did at minus 50 millivolts. Okay, so electrical driving force can change size or strength depending on the size of your membrane potential. Okay. All right, and then the next example is we can change the size of the electrical driving force depending on the size of the charge on the ion. Okay, so if we have our sodium here, and just like above, it wants to come into the cell with those negative charges. And if we have the same minus 50 millivolt membrane potential in the cell, but what if we change the ion? And what if we use calcium, which has a charge of 2 positives instead of 1 positive charge? Okay, so calcium would want to go into that cell more than sodium would, okay, because it has more positive charges than sodium does. So we would draw a thicker arrow for the electrical driving force for calcium as compared to sodium. Okay, just because the calcium has more positive charges on that ion than the sodium does. Okay, so you can see by changing the size of the membrane potential or changing the number of charges on the ion, that can change the size of the electrical driving force. Okay. All right, and then the last force we have is the electrochemical driving force. Okay, and remember, just look at the name and it tells you what you've got going on. So we're just going to add the electrical and chemical driving forces together. Okay, so if you've got an ion, you know you've got an electrical driving force, and then you've always got a chemical driving force because that's your concentration gradient, and so you just add those two together. Okay, but if you don't have an ion, okay, your electrochemical driving force is basically just going to be your chemical driving force, because you don't have an electrical driving force, right? You don't have to worry about that. Okay, so you just have to look at the concentration gradient, and that's it. All right, so those are much easier if you're working with something like glucose or water or oxygen. You don't have to worry about that electrical driving force. Okay, so with this electrochemical driving force for these ions, if your chemical and electrical driving forces are going in the same direction, that's easy. Then your electrochemical driving force will go in the same direction. Okay, but if the chemical and electrical driving forces are going in opposite directions, so like if you have maybe chemicals going in and electricals going out of the cell, then it's a little bit harder to decide, well, which one is going to win here, because they're going to have different strengths, and you've got to know a little bit more information to decide, well, which one of these is larger, and that's going to determine the direction of the electrochemical driving force. And so you're going to need to know the ion's equilibrium potential, which I'll talk about in the next lecture, and tell you how to use that to figure out which one of these is bigger to determine the direction of the electrochemical driving force. So if chemical and electrical driving forces, for example, are going the same direction, you just add them together and you know your electrochemical driving force is going that same way. But electrochemical, if they're going opposite directions, you need a little bit more information to figure that out. Okay. All right, so I'll just do two examples here. And the first one, let's say that our membrane potential is at minus 70 millivolts. So we're at our resting membrane potential. So we'll draw some minuses in there. And let's work with sodium. So sodium is higher outside the cell than inside. And we want to determine the electrochemical driving force. So that's what we want to figure out. Okay, so we've got to figure out, well, what's our electrical and our chemical driving force? All right, so let's start with our chemical driving force first. So remember, that's just your concentration gradient. So sodium wants to go from high to low concentration. So it's going to go into the cell. So we'll just label our chemical driving force with a C. And then our electrical driving force, we've got sodium with a positive charge, and our membrane potential inside the cell here, we've got a negative charge. Remember that opposite charges attract each other. So sodium with a positive charge wants to come in, and the sodium, if it's already inside, says, hey, I want to stay in here. So our electrical driving force would be into the cell. So this is easy. Electrochemical force, when we add these two together, they're both going the same direction. So our electrochemical force, which I'll just label an EC, to say, hey, we've added these two together, then it would be into the cell, and so sodium would move into the cell. Okay, if the cell was at a resting membrane potential of minus 70 millivolts. Okay. All right. Now let's take a look at potassium. So we'll do the same, minus 70 millivolts. And potassium is always the opposite of sodium. It's much higher inside the cell than outside. And we're going to figure out the electrochemical force as well. And so let's figure out our chemical driving force first. So the chemical driving force, just looking at the concentration gradient, we want to move from high to low concentration. So chemical driving force would go out of the cell. And then our electrical driving force, we've got positive charge on potassium and negative charge for our membrane potential. Remember that opposite charges attract each other. So this potassium that's out here would want to come in, and the potassium that's inside would want to stay inside. So here's our electrical driving force. Okay, and notice that they're going opposite directions. Okay, so we don't know which direction our electrical chemical driving force is going to go. Because it depends on the relative strength of the chemical and electrical driving force, which one is stronger, which one wins. That's going to, tell you which direction the electrical chemical driving force is going to go. So we need some more information. We need to know the equilibrium potential for potassium to figure that out, and we can calculate that with the Nernst equation. And so we'll talk about that in the next lecture.